Yeah, so good morning, everybody. So as I was saying, so this is, I just recall the context from last week and maybe remind the last result we obtained. So the goal from now on and from like last Thursday on was to concentrate on a specific problem, which was we are given this family of Gaussian measure on a lattice with lattice spacing epsilon, and then the size is m. So you have m over epsilon points in every direction. Okay. And we wanted, so this is just a finite dimensional probability measure. This is a Gaussian measure. I could even write down the density if you like, but somehow it's not very useful. So I just keep it as it is. So it's the Gaussian measure with this covariance. And then we try to perturb with this local potential. Okay, it's a potential which depends only on the value at a given point. And of course, you have latitude, okay, in the interpretation, because somehow the Gaussian measure, it's a density with respect to the Lebesgue measure. So you could consider, instead of the Gaussian measure, somehow the measure with this density with respect to Lebesgue, and then the Gaussian as the perturbation. Okay, so this in statistical mechanics, both approach works well. As soon as we try to take the limit epsilon going to 0, I think this is the most useful point of view. Okay, because the theory where you take this as the base as the reference measure, it's quite singular in that limit. Okay, it means every point is independent and you don't see very well what's going on. So we take this point of view of perturbing the Gaussian, and essentially we could concentrate on this kind of potential because somehow we want to address the problem in 3 dimensions, and I will try to motivate maybe today that this is essentially, I mean, polynomial potential are the only kind of potential you expect to be able to give meaning to, and higher power are more difficult, and we don't know how to do it. And for the goal, somehow for the objective we had at the beginning, that is just construct a non-Gaussian reflection invariant Euclidean invariant theory in 3 dimensions, that's enough. Okay, you just have to find a potential which gives you a non-Gaussian theory, and somehow you are done. Of course, then you have to study the property and see if this is an interesting theory, but already that it's non-Gaussian would be part of the interest. Okay, then I discussed a bit the history, so let me just remove this. So we have a measure. So let me just rewrite things. Given by the law of a family with covariance, we introduce perturbed if you want. If you have a question with respect to the material of the last week, please ask now. And it's defined in this way, and okay, we will take often. Okay, if you, I mean, some argument works more general. For example, all what we said last week didn't really matter what was this potential. Okay, but okay, let me say, yeah, okay, we will take, yeah, this week or whatever. And B can be taken negative also, okay? As soon as this potential is bounded below, that's fine. And let me remove all this. So this is what we were discussing last week. So I just, brief reminder, we were discussing the Langevin dynamics, first for the linear equation. So this is infinite dimension, okay, finite dimensional in this situation, of the Uhlenbeck process. I recall you that this time now is not anymore the Euclidean time. Okay, it's a fictitious time which we introduced in this context of stochastic quantization. So don't be confused. You could consider the dynamics in the Euclidean time, but then this operator is different. Okay, and of course you have different spatial dimensions. So this, from now on, time is just a fictitious time, and we have this Oster-Uhlenbeck dynamics, and then we somehow worked out that in order to keep the measure we are interested in invariant, we have to consider a Langevin dynamics of this form, okay, where the vector fields were more on top of the linear perturbation, which somehow give the right Gaussian covariance. You also add a perturbation which account for this this potential. Okay, so you have an additional drift, and then the Brownian motion which appear linearly. Okay, so this equation actually you don't need stochastic calculus to give a meaning to it. We saw it, and yeah, okay, we did. I'm just going through the computation of the last week. And I think the main point for Thursday is that we managed to obtain a priori estimate. So let me just, okay, we proved, yeah, so now we decomposed, this will be also important today, we decomposed the solution of the equation in a linear part, which take into account so this is just a Oster-Uhlenbeck process, which take into account the fact that there is a Brownian motion which is driving the dynamics, and then this additional part which actually instead take into account the nonlinear part of the dynamics, if you want. But there is no Brownian source. Okay, it's a random PDE. I don't remember if I wrote it. So yeah, I think I wrote it. Yeah, it's this random PDE. Okay. So, okay, so we had this random PDE, and we found a priori estimates for that, okay, in order to handle the infinite volume limit. Okay, the idea is that they estimate infinite volume, which allows us to prove that the solution do not explode, are not good enough for taking the infinite volume limit, because all the norms are actually growing like the volume, okay, especially the norm of the Gaussian field, and the norm with the initial condition, they grow with the volume, okay? So we introduce a space with weights, and then we just essentially follow the same procedure, but obtain similar estimate, but now only with weights, okay? So this G is this G where you have weights everywhere. And one subtle point, which I skipped a bit, was this point that in the dynamics you have, so this is important somehow, you have to pay attention because it's really meaningful. In the dynamics, when you multiply, you have a Laplacian. So in order to get this positive quadratic form here, you have to integrate by parts, and or sum by parts in this case, because everything is discrete. And these make appear, so this provides some condition, this implies some condition on the row you can choose, okay? In particular, you cannot, it's not obvious how to choose row which are localized in space, okay? Because somehow the fact that you use sum by parts make appear row in different points, and then they have to be comparable. So if in some point, if just row becomes 0 very fast, then somehow the value in different points are not comparable anymore, and you can run into trouble, okay? But the end of the day, yeah, so this was, sorry, this was we get, so this was where we were. We obtain uniform estimates, and somehow these uniform estimates allow to, I claimed, allow to take the infinite volume limit. I will try to write a bit more detail in the, maybe in the extended notes. I don't think today I want to spend too much time on that point, because somehow the idea is like when we, so essentially this tells you that the family of measures satisfy uniform estimate with respect to the parameter m. And then from that, it's not difficult to extract a weakly convergent subsequence, okay? It's just more or less standard probability theory. So if you want the novelty, or the novelty is not even so difficult. Let's say the topic of the last lecture was what are the right estimates and how you get them. And you saw that I hope to convey the idea that it's quite natural. You just you do what you do in PD theory. Okay, you have an equation and maybe you want to take some limit, or you want to understand better this equation and understand the behavior of the solution. Then you try to find a priori estimates on the solutions. Okay, for fixed parameter m, and then these estimates, if are uniform in m, then you can promote them to weak solutions. Okay, and actually you can take limits, and as soon as you have the right estimates. Okay, that's not difficult in this context. These are just a family of ODEs. Okay, okay, so we were at this level. Maybe I wanted to insist very much on the uniform estimate and less maybe in the technology where you take the infinite volume limit. We will have anyway to modify this technology because of the other problem we had. That is, we don't want only to take the limit m goes to infinity, we want also to take the limit epsilon going to 0. And today I will discuss about this, and then on Thursday we will put everything together and try to prove a final result. Okay, but already this kind of result, it's useful because somehow tells you that these measures have some accumulation point. Okay, so let me just remove all this for the moment. This was the old lecture, so you already have the script. Let me see what I want to keep about this part. So, okay, so let me remove everything and then we will see again. So, so last week we saw how to take the infinite limit. Okay, actually better how to obtain suitable weighted estimates. Okay, so this is what I was discussing, which are uniform in the m parameter. Okay. Okay, so I want to mention in the extended notes, I will also discuss a bit which are uniform in M, okay, and allow to prove tightness of the family nu epsilon M. Okay, if you want, so we didn't have epsilon for fixed epsilon and M going to infinity. Okay. Okay, so what about uniqueness? Okay, so what about uniqueness of the limit accumulation points in the topology? So here you have to be careful because the space is like the space of the fields overall, or the full in a non-compact space. So what is the right topology here is the topology of local convergence. In the topology local convergence. So what does it mean? Probability measure convergence against by testing, if you want, with continuous functions on R. So you work these which depend only on finitely many points. Okay. Okay, so they look at the random variable only in a compact neighborhood, if you want. Okay, somewhere.
Excuse me, I have a little question.
Sure.
It's regarding it's maybe a very silly question, but when we say that the function v or potential v of phi, I remember from the last or the previous one lecture, we said that phi was a distribution. So how to make sense of the square of the distribution? Is this some kind of normalized square or something like that?
No, you better ask, because no question are silly. And so here the point is that I was working for epsilon positive. Okay, so here there is no problem, because you see this measure, this is just a Gaussian in finite dimension. Okay, so there is no distribution in this context. You have to imagine that you are working on a lattice of spacing epsilon. Okay, so this is just a Gaussian vector. So in particular, this object never become infinity, because if you look at the expression, it's just a finite sum.
Okay.
Okay.
Yeah.
So that's the context. Okay, so this problem I removed on Thursday. I motivated that there should be a problem, because at the end we want to work in the full space, but that's the reason I introduced these two parameters. So M is because you have this sum which become infinite, and then you don't know what is the meaning of this perturbation. And epsilon is because somehow this object become infinity, could be evaluated in the same point as infinity, essentially, if epsilon is 0. Okay,
but, yeah, thank you.
So remember, okay, so remember that as long as, but you better ask, because yeah, you see this is an important point, and it's the quantity is bounded. Finite sum. You can look at the expression, and it's a finite sum. Okay, because in finite, here we are in finite volume and with finitely many points, lattice point in our lattice. Okay, you have like m divided epsilon to the d points. So this object cannot be infinity. Okay, there is no way this object could be infinity. Okay, it's just a finite bunch of random variables. It's a finite sum. Okay. The problem will arrive today, but yeah, I want just to close like the discussion from the last week. So the last week was only about what happens when I send m to infinity. This is the infinite volume limit, and we said somehow that we obtain strong enough estimates to which are uniform. Okay, so the local, if you want the local LP norm of yeah, we could also resume in the following way. Okay, okay, moreover, in particular, we understood that the local, for example, okay, understood for the local LP norms, or the weighted, it's the same. When you have a weight, then you can localize the LP norm, of course. Okay, LP norm of phi, of the field phi. So this is a field. So now the random variable, it's like this kind of random variable under the measure nu lambda epsilon, sorry, nu epsilon m. So these are LP lambda, but I have finite moments. Okay. Okay, in general, okay, imagine we could resume the discussion of the last week by saying that we obtain estimates of this form. Okay, like we have this polynomial weight, and actually you can do any LP, and then you have this measure, and but epsilon is always fixed. Okay. So we obtain this kind of estimate. Okay, and then you think a bit, and this kind of estimates are good enough, okay, essentially for any p positive. Actually, one can obtain better estimate, okay, by working a bit harder. One can prove integrability, uniform integrability of functions like, for example, exponential. I'm not sure if yeah, surely some exponential of phi. I think you can like something like this, okay, for example, with a weight. Okay, so you have even more than all LP moments you can integrate. So you can integrate like something which in space is in L2, but somehow in the probability space grow exponentially. Okay, in the field. Okay. So just let me close about uniqueness. Okay, so what about uniqueness? Okay, so this essentially proved to you that as soon as you send M to infinity, you can extract accumulation points. In the extended note, I will discuss a bit actually this issue. Okay. And using the same techniques. A similar approach, one can prove that provided V, the second derivative of V is bounded below, let's say this is for some Xi positive, then for M large enough, though of course depending on Xi, 1s, we have also uniqueness of the accumulation of the limit measure nu epsilon. Okay, so but you need more condition. Okay, you need condition on the parameter. Okay, this is natural because we do not expect in general that the limit is unique, and this is linked to the question of phase transition. Okay, there could be phase transition. The model is quite similar to an Ising model, so you could in dimension bigger than 2, okay, 2 or more. So when the potential, so this is saying somehow, you see, this is, think about the fourth potential. This it's okay for us. Okay, the second derivative essentially. So if beta is negative, this potential could be a double well, and then it means that somehow this behaves very much like an Ising model. That is, you have it's preferred for the measure that phi is either a plus a value or minus a value, and then this interaction introduce somehow this covariance in this measure introduce an interaction between neighbor sites. So you have a ferromagnetic model. Okay, so let me say in the model, in this sense it is a model of like ferromagnetic unbounded spin. Okay, if you know what it is, okay. If you don't know, just keep in mind that in general, you could have more than one limit measure. Okay, so that there is no guarantee that you have only one limit. So yeah, so you need a bit more condition. Okay, and actually, yeah, the idea is why this condition is okay. I think I will discuss in the notes if you're interested. It's not very important for us because we will not, in the situation when you send epsilon to 0, this condition we will not hold. So somehow the approach will not work. Okay, but it's not very difficult. You just have to compare the idea to prove uniqueness. You can try yourself. Is to compare two solutions, Z1 and Z2, driven by two Gaussian processes. Yeah, Y1 and Y2, and show, yeah, some yeah, estimates. Yeah, you just have to compare two solutions and somehow show some I know that it's a big vague. Okay, so let me just keep at that because it's not very important. I wanted just to mention, and I will put some notes, some more detail in the notes, and use some coupling approach. Okay, if you know what I'm talking about, that's fine. Otherwise, just ignore what I said. Okay, so today, so what is the plan of today? Okay, today the plan is to address the other problem. Okay, that is the problem your colleague mentioned. That is, we keep epsilon fixed. Sorry, we keep m fixed. Let's say. Oh, if you want, m fixed. So let's say m equal 1, for example, and send epsilon to 0. Okay, so this is the ultraviolet limit. So, okay, so we try to include more and more smaller scale in our model. Okay, so obtain uniform estimates in this limit is more difficult. Okay, and requires new idea. This was okay. So somehow this was the okay. This I mentioned at the beginning. So there are various possible approaches, and they go to the into the name regularity structure. So this was Heirer, which showed how to use this idea to prove these limits somehow. You can use also renormalization group idea. And you can look at the work of Kupiainen in this. I will put in the notes, I will put more bibliography, okay? And or paracontrolled, the idea of paracontrol. These are the three methods I know that works in this context. Distributions. This was introduced by myself with Imkeller and Perkowski. And somehow, yeah, and somehow was some detail were written by Chuk and so the detail about the application to 543 of this idea were developed by Catelier and Chuk. Okay, but I will follow. Yeah, so we, as I told you, if you want the main reference for us here remains the work. So I will follow this last strategy. Because essentially it's the one I'm more familiar with, and somehow deals nicely with the lattice approximation. And I feel that I can try to explain it to you in a reasonable amount of time. Okay. And so the main reference is the paper I mentioned by myself, Osmanova, and myself. Okay. A PD construction. Sorry, don't remember the name. I think it's going to appear, PD construction of Euclidean quantum field theory. Okay, I think it's going to appear soon. Okay. Okay, so this is the goal. So that's the goal for today. So let's try to start. And the problem is what I was mentioning. The main problem is that as epsilon going to 0, the process y becomes a distribution. Okay, so recall. So again, okay, for any fixed epsilon, of course, it's just a function on a lattice, so you don't have any regularity. But the idea is that, I mean, there is no natural notion of regularity. But somehow you are thinking that you are taking a lattice which is going to 0, and we have to understand somehow why does it mean to be a distribution. In any case, you should not expect it to converge to a well-defined function. Okay, so recall that y is the solution to recall our context. So we had a dynamics on X, which can be decomposed on a linear part, and this was the dynamic of Y, and it was more or less like this. Let me write down everything. So this is like m squared, Laplacian minus m squared. Let me put epsilon around just to be sure, and here was like square root of 2 dB. Something like this. So we had this linear dynamics for Y, and the nonlinear part, and the nonlinear part was containing Z, and Z was yeah. And now I'm using notation which are not the same notation in the paper, so I hope you don't get confused. But and the nonlinear part was like this, but instead of having that, we had like minus 1/2. And then let me write u prime, because and you have y plus z, yt plus zt. With actually, I can write v prime here, because really u prime is the derivative, and v prime, it's really just a function of r, and was like lambda phi cube plus beta phi. Okay, in our context. Okay, so I can write it this way. Okay, so this is our problem. Okay, and you see that so this function depends on the space, and all these things are pointwise in space. Okay. Yeah, the computation of y prime is understood pointwise in space. Okay, so we understand this pointwise in space. Okay, so this is a local function. Okay, so what does it mean? I mean that this in a point x, it's really you look at the field in that point, and then you compute this v prime. Okay, which is a polynomial, and so you could even write it down. What does it look like? Let's do it just to be sure we are all on the same page, and it looks like this. Okay, so now, okay, this is the situation. Okay, so it's clear that if, okay, this object you could expand if you want to understand a bit better, and we will have to expand anyway later. So let me write it down, expanded. So the philosophy is the same. Okay, so y is the object we want to leverage our knowledge about and we want to solve this equation. Okay, so this is the difficult equation because it's not linear. And this is the easy equation because it's linear and we know everything about this process y. And so now we have to leverage our knowledge of y to get useful estimate for this equation. Okay, and the estimate we got last week were like using some local of course you have these polynomials of y around. Okay, so for example, if you just try to estimate this, you have the sum over all the lattice points, and you have some power of y. Okay, the problem is that this will not exist. Okay, so let me just write down what is this expression. So this is like 3 lambda, if I'm right. Of course, let's hope I can do it without error, but you have this. And then you have the other situation where you have zeta square, and then we had yeah, this one alpha annoys me here. So okay, let's leave it. Lambda zx cube. Okay, this was good for us. Okay, remember that this was a good term for us. So this term we cannot control the sign, but this term yes, because when we test it, it becomes positive. And then we have this term like this. Okay, so we have beta that and beta that. Now, what is the problem? Okay, so so the main problem is that the expectation of yt of x squared, let's say, you see these objects appear everywhere, okay? So it's a Gaussian process. So is the following, if you want. So let's see. You try to estimate what is the size of this object. And this object give you, so this is the covariance in a given point. So it looks like this. And then we had a formula for that. Let me just recover, otherwise I don't remember, just to remember the factors we had. Yeah, we had this formula. This is 1 because I computed the same point. Let's take m equal 1. Okay, so take m equal 1. So we don't bother. So this is just, we are working in a unit cube, okay, in a unit cube. But this unit cube somehow contains a lot of, you see, contains a lot of points. So when you look in Fourier transform, you see something like this. Okay, so you have a sum over a lot of points, okay, because epsilon is going to 0. This is a large cube of integer points. And you see that that's not looking good, okay, because as epsilon going to 0, this object becomes, so essentially this object converges to whatever, okay, so when epsilon is going to 0, this is, okay, so let me just be a bit imprecise, but okay, it's clear that the domain will become all ZD. And what happens here? Well, you have sinus which simplify, and maybe you can trust me that is not much better than this guy, okay? And what does become? Well, when you take this sum, it will become k squared, really the modulus of k squared. So I could even write in this way. And looks like that, okay? And this object is plus infinity. Okay, actually, you could be more precise, okay? You could even evaluate how fast this goes. And you see that how many points you have here. Okay, you have to consider, so this is going as epsilon to the power minus d. Okay, this is the volume of this cube in lattice points, and then you gain a bit because somehow you remove 2. Okay, so you have like epsilon 2 minus d. If the dimension is bigger than 2. If it's 2, this is logarithmic. So let me just write some cases. So first case, this is if d is bigger than 2, and this is essentially, okay, this behave like prop 2. This behave like this, or behave like log epsilon to the minus 1 if d equal to, okay, d equal 1, it's converging, okay. So you see that we have a problem, okay. If you look at the estimate we got last week, they become useless because you have this phenomenon, okay. So in this sense, this object is becoming a distribution, okay. So you have to imagine that a given point, so this is telling you, which tells us that the typical size of yt of x is blah, okay, so is that. Okay, this is a Gaussian. So if you know the covariance, essentially this tells you also what is the typical size of this object. and this is going to infinity. Okay, so there will be the estimates from last week are useless in this limit. Okay, because they just look at LP norms of LPi, okay, because they depend on LP norms of Ly. Even weighted, okay, because the weight will not change the matter, okay. Okay, so we have to take care to, so this is a problem of small scale. And somehow it's hinting to the fact that this is not a function, okay? It hints to the fact that y is not, that y, let me write epsilon is not converging to a function on Rd, okay? Is not locally, okay, but not locally, not even locally, okay, not convergent function Rd, not even locally, not even locally. So when indeed it will, okay, it will be a distribution. So how we deal with that? So the idea now is that so one possible way to deal with this problem, so one way to deal with this problem and analyze what is going on in the equation, because of course we have to understand how to deal with y, but also then how to deal with this equation. Okay, so this will be our let's say this is the goal now. Okay, so how do we get useful estimate for this equation in this limit, in the limit where y cannot be computed in any points? Because you see that somehow all these objects, the right hand side depends on the fact that I could compute y in some given point. Okay, and that's our problem. Okay, so in the equation that above. Okay, so one possible way is to split all our functions in blocks which are nice. Okay, so this is the idea of analysis in general. Okay, so how you do analysis? Well, you try to identify, you try to look into complex object and separate in simple things. Okay, try to analyze with some way. Okay, so in this context, this is accomplished. Here is accomplished via Littlewood-Paley decomposition. Okay. Okay. Just what does it mean? Okay. We split every function. Remember that we are working on a lattice. Okay. So again, okay, these are just functions defined in discrete points. But since this point become dense, so now you really have to think to them as approximation of functions which are defined in everywhere. Okay. Actually, to a function on Rd, let's note m is equal 1. So actually, we are converging on Td, and Td, remember, just like yeah, okay, it's like 0, 1 to the power d. Okay, so just the torus. So in the today, at least, I will just think to work in a torus. Okay. Yeah, okay, because m it's equal 1 I took. So now it should be something like this. Maybe it's minus 1/2, 1/2, or it's the same. Okay. So we split yeah, in pieces, in very nice pieces. Okay. So every function f, so take a function, so now this is in general, okay? If you give me a function which is defined on this lattice, remember that m is equal 1. So I will not write, yeah, I will not, yeah, okay. Yeah, let me give a name to this, okay. Let us name, define, yeah, lambda prime epsilon, lambda epsilon 1, okay. So this is just, so what it is if z epsilon, so it's this lattice, but you block it like minus. Now I don't remember exactly how I defined. Yeah, minus 1 alpha, 1 alpha. And maybe you don't put one of the point, okay? So yeah, let me call t epsilon, maybe it's better, okay? Td epsilon, okay, good. That's notation, I think it's better. So every okay, now I can split every function in the, so now I have a fixed torus with the parameter epsilon, okay? As follows, okay? So I code these pieces delta I of f. So sorry, this is a bit it confuses with the notation for the Laplacian, but I hope that it's clear from the context. If there is no index I, then it's not this object. But I'm used to them, and I think if I start to write them differently, I will run into problems. So what is this? You look at the Fourier transform. So somehow the idea is that in every this object at the point x is the sum of these pieces, and every piece where lambda I of f of x is, yeah, I'm sorry, they started to work again. Is this, yeah, sorry, no, actually on the lattice I had this expression. So let me just copy what I had in the lattice. So in the lattice I had that. This was 1, for us it's 1, this is 1. And this is this dual lattice, so let me just write is this guy here. And this is just the Fourier transform of f, okay? So this was f, okay? So, so this would give just f. Of course, we had this formula for the Fourier transform, and then I want to just chop in pieces, and I will introduce a function rho. I think I don't have other rows. Rho to ik, yeah, something like this. Okay, so let me where rho is like a function which is defined over all Rd with values in R plus. So this is defined for every R, but of course here you just compute in integers, okay? And is such that so you require from this function, it has several properties. Like one property is that when you sum over all I, yeah, I need another function, but okay. So you have another function. Okay, let me write in this way. So this is one. Okay, it's a partition of unity. Okay, for a nice function Q from Rd again. Okay, to R. So you are doing a partition of unity where you with support in a ball of radius 1, let's say around or around K0, and rho is supported on an annulus. Yeah, of radius. Okay, yeah, like proportional to 1. Okay, so essentially you have you split all RD in a like an onion. Okay, you have a central ball, and this is like the central ball, and then annuli, dyadic annuli, and then you have these nice functions. Okay, all these functions are smooth. Okay, and some other property we don't care about right now. Okay, so this is the splitting. You take this and you take this for, and I'm not sure if you, and when there is this special -1, and for -1 you take just chi. Okay. So that's why I start with -1, okay, because somehow you need to account for this. So all these pieces are in this annuli, okay, so they are annuli, of course, of radius. No, maybe I want -1, sorry. Yeah. Okay, yeah, that's better. So therefore, the Fourier transform, all I think we have to know is that the Fourier transform of this piece is concentrated to the I, okay, and that of the block. These are the little Pali blocks, okay. Block in a ball, okay. Okay, so this is our way to decompose things. Okay, we take this partition of unity in Fourier space. Okay, so this is a nice partition of unity in Fourier space. So that will be the main tool for today. Okay, we just take every function and we split in this way. Okay, I can do for any of my functions. Okay, of course here it's like everything, it's discrete and it's fine. So what I have gained, okay, then, so let me check first thing that does it help me? Well, it's going to help me, of course, okay, because I can now redo this computation for the little Pali blocks, okay. So now we learn that we can use this tool. So let me take just the blocks, and now I compute this for the blocks, okay, and you have the same formula, but now you have this rho I. Okay, let me go to the minus ik here squared. Let me do for positive blocks, and now you see that now this allows you to restrict in an annulus. Okay, so now the size this object is of size. So what is the size of this object? Now the denominator, so everything somehow what is saying to you, let's learn to read this thing. Okay, so this means that essentially you are restricting this integral to an annulus of size 2 to the I annulus. Let's call it annulus I, which is a subset of this set. Okay, so on an let's call the annulus A. Okay, and the ball I call B. So this is just the annulus of size 2 to the I, because I rescaled the argument of rho. And okay, then you have something like this. So surely you can drop the mass, because if you want a bound, so let me bound this. So what happens? Well, what is the volume? Now this is an annulus in the dimension of size 2 to the I. So the volume is 2 to the I to the power D. Okay, that's the size of this guy. And then, of course, you have this factor to the denominator, and K is of size, you see that K is of size 2 to the power D. So this gives you D minus 2, because you have to account, let me just drop this and say this is uniformly looks like this. Okay, I'm not giving a proof, but just giving the argument. Okay, so it looks like this, and you can drop even the mass, because you can drop even this parameter, because when you are away from zero, okay, these annuli are not including zero. So you have something like this. So the volume of the annulus is of size 2 to the I to the power D, and then you have minus 2, because this is of size to the, so the K is of size to the minus D. Okay, so let me see if I can write it here. So this is of size to the E square. Okay, maybe I should use K, but okay, that's the size. Okay, which says that, okay, now I know something. Okay, that so this is of size. Now I know what it is. Okay, it's of size, which is finite. Okay, which is uniform in epsilon. Okay, so this is what I gained. But of course, when I, okay, but of course not in I. And I can be large, okay? And I can be large, because I have to sum. Okay, let's discuss, let's discuss this. So how large can be I? Of course, cannot be very large, okay? Because I told you that as soon as epsilon it's finite, this sum is actually, the initial sum was finite. So what's going on here is that if you look, the partition of unity you take like this, but if you look here, K cannot be larger than 1 over epsilon. So somehow at some point, these blocks start to be zero. Okay, there are no blocks anymore, because there is nothing to sum. Okay, so let me remind, so let's make this remark here. Okay, for epsilon positive, we have, okay, so we have delta I f equals 0 if, so if this is too large, okay, so if this is much bigger than epsilon minus 1, okay, for example, or at least maybe just a bit bigger, okay. So there is a bound in the, somehow the lattice provide a bound. There is not enough, there are not so many little Pali blocks. Okay, so you have to imagine that I is of size logarithm of epsilon. Okay, so we sum over I up to something which is size like log 2 of epsilon minus 1. Okay, so there is a bound. And for technical reasons, somehow you see here the sum stops very abruptly, and for technical reason you have to adjust. Let us define. I don't know if I need it, but okay, maybe I just define this this thing here. Okay, to be this bound. Okay, so. Yeah, so we have that f, it's really the sum over all I from minus 1 up to an epsilon of delta I. Okay, and one has to be careful. There is a technical subtlety here on how one handles the last block, but we will ignore it. Okay. If you see what is the problem, if you see what is the problem, you understand how to solve it. If you don't see the problem, don't bother now. The problem somehow is that for some proper, yeah, okay, so what is nice about okay, I will tell you later about the theory of literal polyblocks, but for now, I think the important thing is that these blocks, at least as far as y is concerned, the random process we have to care about, it solves our problem, okay? Because somehow these blocks now, if I look only at the blocks, they are nice, okay? Okay, one can prove actually that y epsilon converges to a nice infinity random function as epsilon going to 0 for all on the torus, okay, as epsilon goes to 0, okay. So every blocks is very nice, okay. It's a infinity function, and it's even yeah, I mean the Fourier transform it just contains infinitely many modes, okay. So it's a very nice, you can differentiate infinitely many times. It's analytic actually. Okay, so we have this, so this somehow start to help us analyze the problem, because now we never will have to deal with distribution really, okay. Let me introduce some notation. So of course, so now I need to introduce Bezoff spaces, okay, because this would be so what happens to the, of course, you have to sum this function, okay, because somehow in your problem there is a function, there are not just literal polyblocks, and so you will have to deal with these sums, okay. So this decomposition, shift the problem of dealing with distribution to a problem of dealing with large sum. Okay, that's all you gain, but somehow conceptually it's useful to think about it in this way. So I will need some Bezoff spaces. So we say, let's say, okay, so this is a definition if you want. We say that F belongs to the Bezoff space alpha PQ. I'm not sure I need all the index, but anyway, does not cost very much to in the Bezoff space alpha PQ. Bezoff space. If and only if, so you decompose, so of course, yeah, here I'm a bit sloppy about the domain, but these are just functions defined on my tori, okay? And they could be just lattice, so they could depend on epsilon, but let's not bother. If you feel confused, please ask question, but I will try to skip whether I'm working on the lattice or in the full space. So you give me a function and I try to find a norm for it. And maybe this function is a distribution, but somehow this argument tells you, okay, I can always compute these blocks. Okay, this block are nice functions. So I look at the block and then I compute some norm for the block. So these are functions. I could compute LP norms maybe, or L infinity norms. And then I have a number for every block. Now I have to remember how exactly to write this thing, but yeah, and then what you can do, well, of course you have to sum over all the blocks, but maybe you want to rescale the blocks, so you will have an index alpha. Now let me think what I want here. Yeah, I want like this. And then you take, like in the index I, you take the little LQ norm. So you get the number like this, okay? And I think it's fine. And then you give a fancy name to this norm and you call it the Bezoff norm. Okay? And you say it's in the Bezoff space if this norm is fine, okay? So and you take alpha could be any real, and the PQ any positive number, any number between 1 and plus infinity. included. Okay, plus infinity, you just take the supremum here. Okay, so this is the little LP. Okay, if you want, it's like you can interpret this. This is the little LQ in I of the little LP norm. Okay, of this guy. Of this function, the function which from I goes to that. And I could be anything bigger than -1. Okay. Okay, then maybe I don't need to put that here. Okay, so this is our way to measure norms. Okay, in particular, we will use what I call C alpha, and C alpha is just B infinity alpha with norm. Now you say a function is in C alpha if okay, just such that. So what is the really feature of this norm is that essentially you know that the Little-Pali block, so the infinity norm of the Little-Pali blocks is bounded by, just to have an idea of, okay, so what does it mean? Well, it means this, okay? Okay, so when alpha is positive, these are spaces of functions. When alpha is negative, these are just distributions. Okay? In general, okay, of course, okay, of course. All this does not make. Okay, of course, when epsilon 0, okay? Otherwise, it's not, they are defined on a lattice, okay? They are nothing, they are not regular, like, okay? But I just want to, maybe it's even just useful to think, okay, what does it mean to be like in this space? Means that I can decompose the function in nice pieces, and essentially these pieces are going, when I is going to infinity, they're going to 0 exponentially fast. Okay, that's good enough in a first approximation. Okay, when alpha is negative, they are growing, but somehow you control the growth. Okay, they are not growing in an uncontrolled way. They grow just some power of 2 to the I. And 2 to the I is the scale associated to each block. Okay, so from this estimate, okay, so from the estimate above, okay, so from the estimate above on y, one can prove. Now I can tell you exactly, so what is y? Well, y of t will belong to some c alpha. So what will be the index here? Well, you know exactly how it's growing, okay? It's growing like d minus 2 divided by 2. So this will be d minus 2 divided by 2 minus kappa for any small kappa, almost surely for any t positive, for any t real, this object belongs to this space, okay? Uniformly in epsilon, okay? Actually, it converges in this space. Well, let's, okay, keep in mind that you have this epsilon that make everything well defined, but somehow we want to take, we want to take the limit, so we cannot rely on this epsilon. So it's there when you want to think, because it allows you to think, okay, everything is on a lattice, everything is nice, but somehow when you look at a portion of this lattice, the number of points is increasing, okay? So you don't, you have to do something which is uniform, okay? And this is a nice way to look at this object uniformly in epsilon, okay? del infinity norm is the maximum, but instead of looking at the maximum of y, which we know that it's growing as epsilon, we filter y in some frequency. That's what the Fourier transform does, and we look only at this particular range of frequencies or a wave vector of oscillation. And in this particular range, somehow it behaves very well, okay? But of course, the size of the function depends on which range you're looking at. Okay, so you have this, and one can improve this. Also prove that as a function of time, t is continuous and actually uniformly in so you will have uniformly uniformly in epsilon. You will have that y of epsilon belong to a space which looks like the space of continuous function over R with values in this Banach space. Okay, so this is Banach space with this norm. These are Banach spaces. Okay. Okay. Okay, so this is what is y for us. Okay, so in the following, this will be the main property we want to do. So note that we need this case. Okay, is any number, but you see you lose this small k. So in the following, k will always denote an arbitrary small positive quantity. Okay, so this is like small loss due of regularity due to the fact that we want almost sure statement. So this is almost sure, okay, that as a function of t is uniform in epsilon, almost sure. Okay? This is a random variable, so somehow it belongs to this space almost surely, and you can actually construct all these variables in such a way that they converge in this space almost surely. But okay, I don't insist too much on these details right now. So just keep in mind that this you can think. So somehow you see we need probability at some points. This is one of the points. You will need to prove a statement like this, but then we proceed just with this knowledge. Okay, we don't need probability anymore up to the next up to a certain very specific point. So note that when d, okay, now let me discuss. Okay, when d equal 2, okay, we have so we are interested in the two situations. Okay, so the first situation is that what happens when d equal 2? Well, when d equal 2 just in very small, and when d equal 3, okay, you can do the math, okay, yourself. So the regularity is like -1/2, minus something. Okay, so these are the two interesting cases for us. Okay, because maybe I want to use the two-dimensional case to make some example. Okay, so we are now in this situation. Good. So now, in order, let me go back. So we have to deal with our equation. Okay, I'll just remind you, I go back into the equation. Where is the question? Yeah, it's here. So we have to give a meaning to all these objects on the right-hand side of the equation when now we know that y belongs to this space. Okay. So we have to understand what happens to products in Bezoff spaces. Okay. And then you have a fundamental theorem. So products in Bezoff spaces. And then you have a theorem So let me see. No, before giving the theorem, so let me, so I need to handle these products. Yeah, and so what is the idea? So so now we have to understand what happens when I take a product of two functions. Let's say I want to use this norm to control, to have my estimates, okay? So I take two functions in base of space. Let's say I take this in C alpha. I take this like L infinity based space because they are nicer to work with. They are easier, but you can extend the consideration to the others, okay? Then, okay, you want to take the product, okay? And I just explained to you that, okay, you can just decompose every of this function in pieces. So I say, okay, I just write this in this way. This I multiply, and let me use a different index, G. And now you see that somehow your problem, there is no problem in taking product somehow. Imagine that one of these two index is negative, so one of these two objects is a distribution, okay? But somehow in this context, you could say, okay, I can always take the product of every block, and the real problem is, can I make sense? So to give a sense to this product, one has to control the two large sums. Okay. Again, okay, if you are on the lattice, they are finite sums, but you should imagine that they are very large. Okay. So the problem is, if I want to define this product, I need to make a sense of these two sums, and the good way to do it is to split it in three pieces. Okay, so this is the key point now, is that somehow in these two sums there are really three pieces which play different role. So one piece is when I is is smaller than, okay, let me just there is a constant. The other piece is when I is bigger than j plus k with some constant k, and the last piece is when they are comparable. Okay, so this is of size k, okay? Smaller of size k. Okay, so there are three pieces. This case is not very important, okay? Just to say, okay, you have three situations. Either one index is much smaller than the other, either the other way around, or they are comparable, okay? And you give to these three objects three names, and I'm used to give this strange name. Okay, so these are the para product, what is called a para product, and then you have the other one, which is this remind you which function is taken with the lower index. Okay, so here is the opposite. So you have f, and you take the para product in the other direction, and then you have this thing which I denote like this. Okay. Let me see. Can I use? Yeah, there could be this other notation, but I don't like. I prefer this one. Okay. And and call them para products. So now you introduce two para products and the resonant term. Okay. And the key point is that now each of these objects is well defined. So now there is like a kind of theorem you want to prove. The paraproduct are always well defined, and so the two paraproducts are always well defined, and actually they are equal. Okay, so this is exactly G of if you think about it, is G of f. Okay, So let me just discuss one of the two. And the paraproduct, so keep the regularity of the worst term. So this is estimated as with the norm of in the C alpha spaces looks like this. Okay. Okay, let me say I need to be more specific. It's not difficult to prove these kind of things. Okay, just maybe I don't want to spend to do it right now. So the paraproducts are defined in this way, and it's like this if alpha is positive. If alpha is not positive, then you lose alpha, so you have something like this. So if alpha, now I don't remember if alpha is 0, what happens, but I think you can put it. I think it's not a problem if alpha is 0. I don't remember what happens if alpha is 0. Alpha 0 you can ignore, it's not very meaningful. The resonant product is well defined only if alpha plus beta is positive, so this is very important. And but then when it's alpha beta is positive, you have this estimate for the resonant in that case. Okay, so these are the key result, okay, which is not difficult to prove. So let me put it. So the idea now is that to understand what happens to a product, you decompose in paraproducts. And paraproducts, they are called like this because they are better than the product. And why they're better? Well, because they are always well defined. Okay, whatever alpha and beta you have, it's always well defined. So these two terms pose no problem. And this is the term which somehow has some conditions. So let me underline this. And in this case, you have this estimate. Okay. So as a corollary, so therefore, Fg is well defined and continuous only if alpha plus beta is positive. Okay, no, let not me write. And in this case, you have that the product can be bounded by the two norm. Okay, so that's the kind of result you want. Okay. I don't know why. Yeah, it's not in the theorem. So let me put it back into the theorem. Okay, so that's somehow the basic idea we have. Okay, so we are allowed to multiply things only if regularity is okay. Okay, so that's the idea. Okay, only if the sum of the regularity is positive, then you're allowed to multiply two things. But paraproduct and the problem is in the resonant term. Okay, so the product, if you just say what happens to the product, then you don't see exactly what's going on. So it's important to be able to analyze the product into these pieces. So usually one of the two functions is more irregular. In that case, one of the paraproduct it's more irregular, and the other it's more regular. And that, yeah. And but the problem is always the resonant term. Okay. So let me go back. Okay, let me try to use these ideas in our equation. Okay, let's go back with this tool to our equation. Let's see. And this was the equation. Okay, so the equation is this one. Okay, remember it was this large equation, and I want to control the right-hand side. Okay, so in the right-hand side, we have v prime, remember, okay, y plus z, and this was like lambda y cube plus 3 lambda y squared z plus 3 lambda. Yeah, okay. Do you have questions, remarks? So now I want to understand what happens here, okay? And then you have beta y and beta z. And again, okay, the philosophy is that the y I know, okay? So let me put on a side what's going on here, or maybe not. So let me, no, I think I need to understand, I need to understand what happens to y cube. Let's start from y cube, okay? So we said y is a distribution. So by the product theorem, we see that y cube is problematic, since we know y is in, okay, is in C. Okay, let me, regularity of y is negative, okay? Regularity of y is negative. Okay, so you cannot multiply with itself. Okay, that's this theorem does not allow you to do that. So what you do? Okay, so for this term, y is explicit. Okay, so for this term, so one, and we can do a computation, a probabilistic, to prove that y cube converge as epsilon going to 0 to a well-defined distribution, provided it is renormalized. Okay, so here now the point is renormalization. Okay, so let me maybe. So y cube, you don't have much chance. Okay, so it's y, it's irregular, we saw, and then okay, you could define y cube. It's a well-defined random variable as epsilon is positive. As long as epsilon is positive, what happens when it's going to 0? You don't know, and you try to compute things. And the idea is that so there exists a constant, which I don't want. Okay, see. Yeah, let me not such that y cube minus c. So y depends on epsilon. So let me write epsilon somewhere. Minus c epsilon y. Let me see if maybe I want to put a 3 here for some reason that will become apparent late. So let's call this y epsilon. Sorry, let me give a name to that. Let's call it y epsilon cube. The random field. So y epsilon cube is something which depends on a parameter x. Okay, what you're doing, well, I take y epsilon x, depend also on time. So okay, let me, I'm not sure how to write it. Let me write in this way. Okay? I'm not sure the notation is the perfect one, but just to understand what I'm doing. So I'm computing something at a given time, and you subtract exactly that. And then here you have a random field. And this random field converges as epsilon equal to 0 to a random field in. So it's continuous in time with values in C. And now what is the regularity? The regularity here, it's like 2 minus d over 2. Sorry. Yeah, I always get it wrong. Yeah, that's not. Yeah, that's. Yeah, I always go too fast. So So let me not discuss this first. We have the problem y square. So let's discuss y square first, because of course for y square it's easier. Y square, you can do this. So this converge to a random field y2 in, and then this is the regularity. Let's give a name to this constant because it would appear often. So let's call it, did I have gamma somewhere? Maybe alpha, to alpha minus kappa, okay? With alpha equal 2 minus d over 2, okay? This was the regularity of y. Alpha, so regularity, this was alpha 2 minus d over 2 minus kappa. But there is a kappa, but let me put the kappa, let me try to put it here. Okay, then here we have 2 alpha. Okay, I think it's okay. Okay, so this is always negative if d is bigger or equal than 2, okay? Okay, so that's, if you want, there is a lemma, or if you want, it's a theorem. Okay, here in probability, law, let's say, law. Just to say that you are, then you can make it better, but let's say that you have this random field and it converges in law to a random field with this regularity, okay, still negative. So it twice alpha, so alpha was negative, so this is even more negative. For y cube, you would like to say similar things, but you have to pay attention similarly. So y cube, it's more complicated because it will not converge if it will not converge like this, but somehow let me see what is the useful thing to say. So to a random field, but now this random field somehow is not continuous function of time. You need, let me write in this way, minus kappa, and then you have 3 alpha, something like this, okay? Where C minus kappa is a space of distribution in the spatial variable, in the time variable, with negative regularity. Okay, so that what I'm saying is that, okay, it will converge if you're able to somehow, if you're able to test in the time variable, okay, alternative. So things like, so for example, if you can smooth out the time variable, will converge, okay? But okay, let me, so this is the only difficulty. If in first approximation, you could think that a similar phenomenon happens, but then you compute and you realize that there is a small problem here, but you just lose a bit the time regularity, and then it's fine. This will not, so it hints that we have some more problem here. Yeah, in 3 dimension actually. Yeah, let me, yeah. In 2 dimension would be, yeah, sorry. Okay, let me say if, let me say if d equal 2, then here you have a nice statement without anything. While if d equal 3, then convergence holds in C minus kappa. Okay, you need a small kappa. Okay, so, and I don't say anything about d equal 4. Okay, you need some space. Okay. Okay, so these objects somehow are dealt with. Okay, so this theorem tells us that provided we found this constant. So let me say something about this constant. Moreover, so C epsilon goes like epsilon to the alpha. Okay, I think. Yeah. Now you see somehow this constant looks like. I go back because this constant somehow looks like the problem we had at the beginning. Okay, looks like this. 2 alpha then. Okay, so it looks like C to the 2 alpha, and actually this constant you can, for example, fix it to be like yt epsilon, exactly epsilon square. Okay, which is uniform in space. One can take. Okay, that's our choice. Okay. Yeah, actually, it's not alpha. There is no kappa here. So let me be precise. It's d minus 2 minus d. With the understanding that when d equal to this is logarithmic. Okay. So that's the statement. That's somehow the idea of renormalization, at least in this very simple context. That is, okay, your object of interest does not have a limit, but you can subtract something and it will have a limit. And now one could start to ask, okay, where I find these things to subtract, and you see that I mean, that was more or less the reason why I was bothering myself to have beta all around, because somehow this could provide this constant. Okay, so now we see. Okay, so we see that replacing. So if you replace beta, now you replace beta with beta. I need plus or minus. Sorry, let's put minus c to the epsilon. Yeah, maybe even 3c plus epsilon, 1s. So if you just replace beta is a parameter in our problem. Okay, so you need, or let me be precise. Okay, let me take beta prime plus minus this. Okay, so this v prime now looks like, okay, so I put beta prime, then there is minus epsilon. Sorry, I need to put lambda. Let's see if I can manage to get the right quantity. Then I get really 3c epsilon y here. And when you do for here, for z, you get exactly what you need here, because you get minus c epsilon here. Okay, so that's somehow quite magical at this level. And you can, yeah, I mean, you can write this as a, now you can say this is lambda y cube plus 3 lambda y square z plus 3 lambda, and now you have this constant, okay, plus 3 lambda, let's call it y1. Oh, yeah, no, maybe y1. Just to be uniform in the names, okay, with y1 just equal to y, okay, just to be. Okay, so now somehow we manage, so that's a choice we made, okay? We made the choice that we take the coefficient beta to depend on epsilon. There is no reason why we don't allow, okay? Remember, what is our initial goal is to find something that works. Then this sum, there is no reason why I perturb with something which is constant in epsilon or in the parameter. Okay, I can choose lambda. I could even a priori choose lambda, which depends on the parameter. As soon as when I take the limit, I get something interesting, that would be fine. That's was my original goal. So in this context, there is no reason to fix the parameter one way or another. Okay. there's no even reason to take a fourth order polynomial if you want, but somehow if you start to think about this problem and then you take higher order polynomial, you see here we start in 3 dimension, we start to have problem already with like cubic polynomials around here. So as soon as you try to take higher and higher order polynomial, you run into more problems. Okay, so in 3 dimension, you want to take something which is not quadratic. Cubic you don't like because they will not be stable, and then you have to take a 4th order polynomial. That's the first choice, and somehow you cross your finger that things works and things are going to work. There are, of course, you can make reasons for that because somehow the theory is still subcritical in some sense. And I could try to explain this as soon as I get something which I can analyze. So let's me proceed. But you see, I changed it in such a way that the parameter I introduce go together with the object that create the problem. So here and there. So this is like y cube. And this is y square, and somehow what is a bit magic is that things are working out because you have only one constant. So one magic, so one constant works for both difficult term, problematic term. Okay, so that's somehow the thing one should understand better. Okay, there are reasons for that. I will not namely super Reynolds-Miller or subcriticality of this model, but I will not spend too much time to discuss it now. Okay, I just want to have the work done and then we can discuss the why it's working. Okay, so far I just remind you that there are some magic in this theorem that tells you that the same constant work here with different parameters, and somehow things add up quite nicely at the level of these polynomials. Okay, so the things appear with the right constants around. And this makes, so now I have very well-defined objects here which converge. So now let's see what is the next problem. Okay, so the next problem is this. Okay, I have 2 order of problems. So now I know that this is not converging as a function in time, but I don't care very much because this is in a differential equation. So you can think about integrating in time. That's fine. Okay. But now I have this kind of problems around. So so next problem are the products here. Okay, the products. So I have 2 problems here. I need to care about what happens to these 2 products now. Okay, and then of course maybe I could even have a problem here, but for that I wait to see what's going on because it's not clear what is the regularity of Z, but it's clear that here there is a problem because this is negative regularity. Okay, this is a regularity alpha to alpha, and this is a regular which is negative in 2 and 3 dimension, and this is a regularity alpha. Okay. So in order to understand these products, yeah, sorry, there is, yeah, I think, no, it's okay. Okay, so this is really zeta square, okay, while this is just a name for these objects, which looks like the square, but it's not really. Okay, it's the renormalized square. So renormalized, so square. And here, the renormalized cube, whatever. Okay. Okay, so I have to understand this. And so what is the regularity of Z in this context? So now I can hope, so what happened? Okay, let's try let's try to get some estimates for Z. Okay, so we test the equation with Z and integrate in space. Okay. Okay, so this is the next step. Okay, try to find a priori estimates. Yeah, weak ordering. Yeah, so I could renormalize square the weak ordered, of course. But I mean, it depends the choice you make. Okay, with this choice is weak order. Okay, with this choice, the renormalization corresponds to weak ordering. Okay, if you know what is weak ordering. If you don't know, you don't have to care. Okay, just you have to know that one can prove this theorem. Okay, and if you choose this constant in this way, then you're really weak ordering. But any constant which behaves asymptotically like this, it's okay, and then it would not be the weak ordering. Okay, anymore. But it's not very important at this level. Okay, so what happens if I test? Okay, so remember that if I test, I will have some. Let me write this sum as an integral, because then it's clear that somehow looks more like the. So you will have z square integrated, and maybe now I need to take the derivative in time, or even the partial derivative, let's say, and 1/2 maybe. So if you look again, okay, you test the equation. Okay, the equation you have, you see here, okay, you have the derivative in time. Actually, the equation, it's really the derivative in time. Sorry, I was, this is really not even, this is really a derivative. Okay, so you multiply via z here, then you integrate, and of course it's a sum. Okay, you are on a lattice, but somehow you get an expression. Let's see how does it look like, the expression. So I go back. So how does it look like? Well, you have this, then you have what you have. Well, you have summing by part. You have really nabla. Again, okay, there is no weight, but things are periodic, so you really have this squared. Let's see if you have 1/2. No, I don't think so. And then you have the mass. And then you have z square, good. And then you have lambda. Then you have this term cubic, which become quartic with the right sign. So I think you get minus z4 if I didn't. Okay, so you have an integral of all these things. This everything at time t. And then you have things in the right-hand side. So what you have in the, this is all summed over, of course, okay? And then what you have on the right-hand side, let's see. Well, you have this, certainly. So you have 1/2 because maybe minus even, I don't care very much. This you don't care because you don't have any sign, and then you multiply via z. And then you have this, z square, and then you have, okay, now you got what I hope you got. Okay, you just multiply with z and you integrate, and then you have these two other terms. So let me maybe write it in the second line. Okay, so this is what you would do if you want to do some a priori estimate. So you will get something like this. Okay. And again, okay, if you remember what we did in the infinite volume limit, here the game now to play is, can I estimate? So you see, these are the good guys. So these are positive quantities which you can use to estimate. So you have to estimate this. You have to, because what you want to know is that this quantity do not grow too much in time. So you want an upper bound on this side, and this side does not help you because nothing inside here apart from that term. The term is not positive, okay? It looks positive, but y square is not positive, okay? I go back. y squared is y squared, which is positive, but you subtract a constant, okay? And this constant is positive. So this term is not positive, okay? That's part of, generate a lot of problems, actually. In particular, let me mention, related to before, you see that beta is not bounded below, okay? Because this constant is diverging and it's positive. Okay, so that's a problem for uniqueness in this context, for example. Okay, you cannot do what I said at the beginning of today's lecture to have this convex or bounded below second derivative for the potential. But okay, let's skip that. So how I can estimate this, and you see that now I run into problem because somehow what you know about Z, okay? So the right-hand side, so the left-hand side tells me that I have control of the L2 norm of Z, of the L2 and L4 norm of Z, okay? These are these two terms. This is the L4 norm, this is the L2, but the L2 you can control into different ways, either here or here. It depends what you want to do. And you can control, but also of the like H1 norm, okay? So this is like the lattice H1, but it's the H1 norm of Z. Okay, so for Z you have some regularity, okay? This means we have some regularity. For Z. If you think this is a parabolic equation, so you should really expect Z to be more regular than that. But in this approach, we only exploit these a priori estimates. So at this point, you only know that you can control this derivative. Okay, so you should imagine that you have H1, and if you check, okay, so note that, so H1 is really the Sobolev space H1. Okay, so H1 in this context is essentially B1 to 2. Okay, so in the Bezoar space, okay, in the Bezoar scale, Bezoar scale, we have all the Hilbert space valued. We have we have Sobolev. Okay, we are, I mean, at least this Sobolev space, okay, the Hilbert space valued Sobolev space. Okay, so we can control this, and I didn't told you, so the product, the theory of products and paraproducts extends naturally to Bezoar spaces with indexes order PQ other than plus infinity. Okay, this was what I told you. I told you the case of the C spaces, the C alpha spaces. But of course, you can do similar consideration for any pair of index. But I didn't wrote it down because then you have to take into account integrability. Okay, when you make a product, the integrability degrades because you have order inequality. So it's known. Let me summarize what I'm arrived now. So I want to handle this equation now, okay? And you see that, so now the point is that we can assume Z is H1, but does not help us. So it helps us, okay, now we have to, okay, let me maybe summarize. When D equal 2, we have that essentially Y3 is in C minus 3 alpha, and Y2, sorry, so YK, let me write it this way, okay, YK is in C minus alphas with K 1, 2, 3, and alpha essentially minus K, a small negative quantity. Therefore, all the products in this formula, in the a priori estimate, right-hand side, are well defined. Okay, so this any product here, it's well defined. Okay, assuming Z in H1. Okay, so because essentially the regularity, the sums of regularity is positive. Okay, because this here you have 1, and here you can assume that alpha it's really a small quantity. So here you have k. For example, one has estimate like, so this essentially solve the problem in 2 dimensions. Okay, because okay, you can estimate this object. This object will be estimated in a negative subole space, but you don't actually, you can estimate the integral. Okay, so this is like a duality. It's not even a norm. Okay, so you can estimate this integral, and you can say, okay, this integral, it's like not the L1 norm, but it's the duality. So this can be estimated by like y cube in C minus 3 alpha. And here you have choice. Okay, essentially you need just to estimate Z in like, sorry, 3 alpha. Like here you need something positive. So for example, you can estimate B alpha alpha 1 1, because somehow this is infinity, this is the duality. So you can estimate 1 1 here. And you have similar estimate for the other terms. Okay, something like this. So this is the usefulness of these spaces. Now here, of course, you do the same. You estimate in 2, and here you estimate base square. In you need a bit of sorry, here you need minus because alpha is negative. Yeah, let me write like 4 cap, and here like 2 cap, 3 cap, just a bit more than 2 because you need a positive. And similar estimate for the one with 1, and here you have 3, and here you have 1. Okay, this is not a very funny game right now, because now you understood more or less what you want and what you do with that. Okay, so these are just estimates, so they are good with a constant. So this is the theory who tells you. Okay, but you believe somehow that okay, somehow it's not very unbelievable. Okay, the regularity has to be positive here, the sum of regularity, and then somehow here you have to imagine that these are like L infinity space, so you need L1. Okay, if you want to have a duality here and here too. And then of course this is, I told you, this is okay. So what you do with that? Well, you need L1, so you can use L2 because you're in a bounded set, and you need some regularity. So here you have a choice. So here you can choose actually to use, like, you need some regularity, so you have to use the L2 norm, like something like this, but you need only a bit of that, and the rest you have choice to use, for example, the L1 norm. Okay? So something like this, the L2 norm. Okay, something like this. Okay, and for some small delta, so you just use Young inequality as standard inequality. So what happens here? So let me finish with that, and then I stop. Here it's trickier. So you have this. That's fine. Maybe it's yeah, maybe it's not good doing like this. So let me just say that you can split things, and here maybe, okay, here you can here, yeah, you have to pay a bit of attention. So now you want an estimate. There should be some index. So for some positive power, no, let not use k. Positive power, yeah, I used all the variables. So let me use k, something like this, okay? And this you can, something like this, I think you can, because you take a high power, so you don't need to take a very high power of Z, and then you can use something like this. I think it's working. And some k bigger or equal, some large k, okay, whatever. And here you want to do the same. So I will show you why it's important. So something like this, okay? You don't really need, don't want to be precise right now, okay? You can be in the paper, but here it's the same, okay? But here you already have Z square. So you have to pay attention, because if you want to split this, you have power bigger than 2. So you cannot reabsorb in the L2 norm, and here you have to use the L4 norm. Okay, that's where it's important to have available the L4 norm. Okay, and I think here you can take a small constant if you're willing to pay a big constant here. Yeah, I think here always you can take a small constant. And you pay a big constant here. The same here. Here it's even worse, okay? You have to remember that you have, on the right-hand side, you have at most the 4 power of Z. So here you have already 3 power of Z. So if you're not careful, if you get something which is more than 4 power, then you are lost, okay? So here you have to be careful, but more or less you get somehow the same kind of estimates, okay? You get something like this, and you need a bit of regularity, and you need the integrability, okay? So then maybe, okay, here you don't need, but it's not very important. So overall, we have, so overall what you have, okay, you have that the right-hand side, it's smaller than something, okay, I can handle also these 2 terms, they are not very important, and you can handle. So essentially you will have a function of y plus a small, let's say, okay, plus so you can have you can obtain. Let me write just what we obtain. You say where yeah, qy is just some random. So it's just some random constant times these polynomials. Okay. Sorry. You just define some random constant. I mean some constant times this polynomial. And this you have maybe some for k 1, 2, 3. Okay, something like this. Okay, and this is a good a priori estimate. So here I have k. Why I will tell you soon. Okay, so into the equal to. Okay, let me stop here because I'm already out of time. So